Okay, so today we're going to be looking at the Peterson reaction. It is a reaction which is useful in forming carbon-carbon double bonds. Conceptually, it is just the elimination of a silane, trimethylsilane, and an alcohol that are next door to each other in a molecule. And we can do this using either acid or base, and we will get a carbon-carbon double bond that would look something like this. The important thing with this reaction is that it is a stereospecific reaction. And what this means is that the way that the silicon and the hydroxy group are removed from the starting material happens in a very carefully controlled way. And either there will be one of two options. There'll be either a Syn elimination or we will have an anti-elimination. Syn elimination is typically controlled by base, so I'll just color in blue over here. Anti-elimination is normally done with acid. Why this is important is whether we have a Syn elimination or anti-elimination means that we need to know what the chirality is of these two centers that are sitting next door to each other. So as an example of a Syn elimination, I'm just going to draw out this as an example. So we take the same compound that we started off with over there, but we're going to put the silicon group, the trimethylsilane, and the alcohol on the same side, just to make it easier in terms of drawing out this mechanism. Now, the base that we would use, and a good example of this would be a hydride, for instance, something like potassium hydride. And potassium hydride can then react with the alcohol, H-, and pick up the H, and the electrons end up on the oxygen over there. So the immediate intermediate that we will get is an O-, alkoxide, and we've still got the silicon over here. Then what happens is that the oxygen attacks the silicon and you get a 4-coordinate intermediate, very much like the Wittig reaction which we've already covered. This 4-coordinate intermediate can then undergo an elimination reaction, again very similar to the Wittig reaction. So the silicon carbon bond can now donate in to give a carbon-carbon double bond. This bond needs to break and the electrons end up on the oxygen over there. And so our product will be the alkene, in this case the cis alkene, because both of these were on the same side to start off with. For anti-elimination, the two leaving groups need to be on opposite sides, and the mechanism of this goes something like this. So we just take just an alkyne chain like that. We can put a silicon facing down and an OH facing up. Now these are under acidic conditions, and the most common acid that's used in this reaction is H2SO4. Typically this is just done in a water and THF solution. So we use the H2SO4. The first thing that's going to happen is the H2SO4 is going to protonate the OH. This is a sort of acid-base chemistry that you should be familiar with at this level. So we're going to get OH2+, making this into a good leaving group. It's not just going to leave straight away. It is helped along by the removal of the silicon group. They need to be opposite each other, anti-periplanar to each other, but the water that's present, H2O, silicon loves oxygen, just as before in the Syn elimination over here. We've got oxygen loves to pick up that silicon, which is like a giant proton. We can pick up this proton and kick out water like that. And this happens in a stereospecific manner. And so, because these are on opposite sides, we should be able to work out that the product will be the trans alkene like that. It's all very well knowing that a Peterson reaction is either a Syn or anti-elimination type reaction. We just need to make sure that when we want to work out the stereochemistry of the double bond, that we do it correctly. When we look at our line diagrams like this, which are flat, it can sometimes be difficult to make sure that you can see whether the reactions are going to go from the same side or opposite sides and how the structures look. It's much safer when we do these types of structures in order to work them out to use a Newman projection for that. So for instance, if I had to take this reaction over here and I said that we were going to use some H2SO4, so now we know that we are using the acid mechanism, so it's an anti-elimination. So what we need to do is we need to get the silicon and the OH into opposite sides to work out whether we're going to have the cis or trans stereoisomer. So the Newman projection is a fantastic way of doing that. So either we're going to look down this bond over here, the silicon and the carbon that's got the silicon on and the oxygen, we either look down this way or we're going to look down that way over there. Really doesn't matter which way, and I'm going to do it this way. What I suggest is that I stick my eye there and look down that bond like that. What I suggest is you try and do it the other way as well, just to test that you can do this properly. So as I'm looking in the plane of this paper over here, down these two carbons, the first carbon I see is a point in front of me. The other ones that we know what we're doing about is going to be a circle behind. As I'm looking at this carbon over here, in the plane of the paper, which is going straight down, because this is the plane of the paper going straight up and straight down over here. In the plane of the paper, this ethyl group is coming straight down, so the other bits are going to be like that. And behind this ethyl group over here is relative to where I'm putting my eye, is going straight up. So it's going to be there, and all of these are going to be, because they're trigonal planar, we can fit in the rest of the Newman projection like that. So we know that this is an ethyl group, and this is an ethyl group over there. Now remember, as we're looking at this Newman projection, this is the plane of the paper, the two ethyl groups. Everything on the right hand side relative to what I'm looking at over here is going to be below the plane of the paper, and hopefully you can see that. So both the OH and the silicon are below the plane of the paper, but on everything above the plane of the paper, in this diagram, is everything on the left hand side. So in the first carbon below the plane of the paper is the OH over here, and the carbon behind the circle is the silicon. All right. So at the moment, the way this has been drawn out, two hydrogens, the silicon and the oxygen happen to be on the same side, and that's not going to help us. So we need to swing this around. We need to get the silicon into this position over here, or the oxygen into this position over here, and we can do either one that we choose. So we just redraw the Newman projection, and let's keep one of the sides the same and the other one different. I'll keep the front the same. So we've got ethyl, we've got OH, we have H, and we need to get the silicon over here. And in order to have got the silicon over there, we've turned this clockwise, the back ones clockwise by 120 degrees. So that puts a hydrogen over there, and it puts the ethyl group over there. All right, and so now when the elimination happens, which happens by, first of all, we need to protonate this one over here. So we're going to get a positive. We need the water to come in and collect the silicon. The silicon carbon bond, which is at the back there, is going to come and form a double bond. It's difficult to show that, and then this will break over there. So this is an anti-periplanar elimination, all right, which is the way that this needs to occur. And once we've done that, we should be able to see now that in the product, the double bond, we'll have the two ethyl groups on the same side, we'll have the two hydrogen bonds, or the hydrogen atoms, sorry, on the same side. And so when we draw out our product, it's going to look, here's the double bond, so the two ethyl groups need to be on the same side, and the two hydrogens. So this would be the major product from this, the acid Peterson reaction on this one, which may not have been obvious to have seen had you looked at this line diagram over there. which is why the Newman projection is important. All right, so perhaps go and practice that. Try this example again, but draw the Newman projection looking from the other side and making sure that you work it out correctly. Being able to draw the Newman projections is actually a very important skill in organic chemistry.